Glad to be here again in the beautiful Bilbao, nice city, nice region of Spain. Today I'm going to start this session a little bit higher level, and I think it will nicely connect to the next upcoming presentations of the speakers, because they will be diving into some specific applications. I'm going to start zooming out a little bit, and I'm going to try to shed a couple of lamps or some light on the digital forest, because today a lot of people in the water industry talk about digitalization. A lot of people talk about how to handle it, what can we do with it, but we still have a lot to learn, and there's still a lot of confusion. For example, we have a lot of tools we can use. There are a huge amount of different tools in the digital space, but only few people have a very good view on that. And fewer people have a very good view on the applications of those tools. Yet it's so crucial for successful digitalization that we understand which tool to use for which application in order to have the impact digitalization can have. Yeah? So this is a little bit the topic of my presentation, to shed some light on that. I'm Wim Oudenaert. I'm CEO and co-founder at AM Team. We are a Belgium-based company, and we work with utilities, engineering firms, and also technology companies worldwide. So let's start with an AI-generated picture. Yes, here you see it. These pictures are so beautiful. You can keep generating them for hours. Let's look at so I tried to generate a picture of the integrated water landscape. So integrated means everything is connected. Drinking water, wastewater, reuse, sewers, networks, catchment, really everything is interconnected. In the past, we were handling everything as silos, but these things really come together way more. And what are a couple of these challenges in the integrated landscape? They are coming at a very rapid pace. So some of them are very obvious. Climate change mitigation, climate change adaptation, very big topics. Maybe a couple of years ago, not that big topics, but today they are being felt acutely, and especially in the adaptation stage already, a lot of people, utilities, are looking into that. We have to design future-proof, because our infrastructure in the water industry lives for 20, 25 years. Now the question is, in this dynamic world, how do you now design for this? It's becoming very, very complex. So we need to take way more complex decisions faster than ever. And this is very difficult, because the decisions taking them is already difficult. Now they become more complex. We need to address them more urgently. So this means we need a couple of new digital tools that we didn't have or didn't use in the past. This is a huge challenge here. Aging workforce. Utilities are literally exploring digitalization to store the knowledge of experienced people that are about to retire. But on the other hand, you cannot fill this gap equally fast with new people. So you also need new tools to train these people, to upskill them way faster than ever. So at both sides, the outflow and the inflow, we can use the power of digital. When we look at drinking water, well, we need to look into different water sources, new water sources. When we look into wastewater, we need to address new regulatory concerns. So all of these things are happening all at once, all in the same decade, let's say. So it's quite some challenges. So I'm not going to go over these challenges again here. So you can see them on the left side. We have emerging challenges. But on the other hand, this is the topic of this conference, the Digital Water Summit. We have a lot of emerging technology. And this is creating a lot of opportunities. For example, we have AI. Everybody talks about AI nowadays, and it's having massive applications in the water industry. We are having more and more computing power, very good mechanistic models, soft sensoring, cloud applications, security, an ecosystem that starts maturing. And at this summit, it will become clear that it's still maturing. We need a mature digital ecosystem. We need to know what to buy, who is providing what. We are far from that, so this is really crystallizing, but at rapid pace. Now, when we combine emerging challenges with emerging technology, this is giving us a lot of opportunities. Let's zoom in a little bit about emerging. What does emerging mean? Well, for example, when you just Google You can do that on Google Ngram. The use of the phrase digital twin as function of time. This is the graph you see. So you can see something is happening. This is not really exponential, it's kind of vertical. Huh? So something happens here. So we cannot neglect the fact that digital twins are just on the rise. They are going to have a massive amount of applications in the water industry. There is part of a hype, for sure, but there is certainly a lot of sustainable value in digital twins. So just to give you an idea what emerging means, it's going extremely fast. You can do the same with AI, you can do the same with soft sensors, you can do the same for all these phrases. So let's go back to this figure. If you combine both, you have a massive business case. And this is really what we need to understand in the water industry, the business case of digital, because it's not easy. It's not easy to digitalize the water industry. We are having a very complex industry compared to many other industries. For example, one example, every country has different regulation and there is a lack of standards. Every treatment plant is different. Just 2 examples. So we need to understand these benefits because this will allow us to have the drive to go for it and to understand that we can really solve a couple of them. Smarter plants, making better decisions faster, communicate better in big organizations, prepare for change. So this is literally the crystal ball, conduct what-if scenarios to really do climate change scenarios in the future, and training of people, upskilling, storage of knowledge. So these are massive business cases when you look at it. So actually, digital water is the space where these opportunities meet the challenges. So we don't digitalize for the sake of it, but we try to really solve big issues. And the water industry, I think everybody agrees with me here, is a very crucial industry. So we need to really be on top of this game. When we look at the core of digitalization, for example, a smart treatment plant, the core of it, compared to a conventional SCADA system, that exists for decades, right? You send some sensor data to a SCADA or to a PLC, and you do an action. What is the big difference is that you will bring in some additional layer of intelligence, a model, a artificial brain. Can be AI, can be a mechanistic model. And actually, these are the 2 families of models. Not very well understood, but crucial to understand. On one hand, we have the knowledge-driven models. They are called the mechanistic models, in fact, knowledge-driven models. I'm just naming them knowledge-driven because we can easily compare it with data-driven. So these models are based on physics, biology, chemistry, known laws. They are published equations, yeah? So for example, kinetic models, physical models, there are a lot of them. And on the other hand of the spectrum, you have the data-driven models, which is based on a huge amount of data. And you start training algorithms. It shouldn't be AI all the time. It can be statistical models, can be a simple correlation, but it's black box. Okay, so you train a model based on data. And in between, you have hybrid models, which have a huge potential. I will come back to the potential. Examples. So this is a slide on examples of mechanistic models. We see some treatment plants. This is a wastewater treatment plant. This is another system at the plant. So this is a bioreactor, a biological treatment process. And this is an ozonation system, which is a chemical treatment process. So there are mechanistic models that can predict what's happening inside. One example from our business, this is a CFD model, which is these very colorful 3D graphs. It's a physics-based model where we add, on one hand, the biological kinetics. In this case, we are predicting greenhouse gas emissions. For example, the red spots here indicate greenhouse gas emissions, or ammonia, or effluent quality, or energy. And in this case, in this chemical process, you are predicting byproduct formation, how much should you dose, okay? So these are mechanistic models. And of course, they are proven. They are being used for a long time already to design such plants, but now they are emerging as operational digital twins as well. Yeah, here you see a couple of these benefits. They can be really massive, yeah? Proper system design. Let's go to some examples of data-driven models. I'm not going to mention machine learning AI here because I just assumed many of the talks here will talk about such applications. A very popular one is drinking network modeling, okay, where you have a lot of data. So I'm going to focus on some different data-driven tools. For example, predicting membrane fouling, the difference between reversible fouling, irreversible fouling, or a coagulation process, quite complex. You are predicting the turbidity, the falling speed of a filter, and you can save some coagulants, some chemicals. So these are two applications of data-driven mechanistic at the treatment sites and the differences of them. So this is trained on a huge amount of data, and the previous ones were mainly informed by known equations. So how can they work together? And if we look at today, where can we already find the best applications? Because this is really where we should start. Well, when we look at data-driven models, many of these beautiful applications are assets. For example, you monitor the pump vibrations and you try to predict the failure in the future of a pump. A lot of quality data, a lot of high-resolution data, very complex to model that with a mechanistic model. So you give it to an AI or whatever equation, and it predicts the asset health. Drinking water networks, sewer networks, another very nice area. When we look at knowledge-driven models, I think they have a huge potential at the treatment sites because we have a lot of pre-existing mechanistic models there. And you can also combine them, of course, in hybrid here. You can bring in some mechanistics here. But just saying that currently the very successful playing fields of these tools are in the highlighted regions. So then what are the pros and cons of both, and where are the synergies? If you want, just like running a business or a team, if you want the best team or a football team, whatever team, you need complementary people. People that are preferably very different, but that can really complement each other. And actually, these both tools are not a substitute for each other, but I think they are very, very complementary. For example, when you look at data requirements, the data-driven models need a lot of long-term, high-quality data. You need to train them. On the other hand, knowledge-driven models can work with very limited data because they have pre-existing knowledge. They are more generically applicable across plants. And maybe lower quality data, because let's remember the water industry and especially wastewater treatment has a lot of low quality data, low resolution data. The required skills here are way less because you just give it some good data and you have a model. While at this site, you need to have the expensive knowledge, like the extensive knowledge. So that's a con. Trust by humans. Well, this is a black box. Often we hear from operational people or from technologists, yeah, this data-driven model just spits out some values, recommends us what to do, but it doesn't say why. And people, if you read a lot of psychology books, we always want the why. That's human nature. This is more of transparent, and you can really see why the model recommends something. Here, the adaptability of the model, it's automatic and maybe infinite. Give them more data, and they can become better and better and better, maybe forever. That's a very big benefit of data-driven models. While these ones, of course, a human needs to recalibrate them, needs to extend them, needs to adjust them in order to keep them in a good shape. And when you look at the application freedom, well, these are mainly limited to the conditions the models have seen, even though you can argue that. There are a couple of applications of that. But what's not in the training data set is very hard to predict. That's why these models, the mechanistic models, are way better at, right now at least, for what-if, long-term, crystal ball, simulations, looking into the future. Couple of examples. So this brings us to some closing remarks. I think, so this is a screw and a nail, all right? And I think this is not going to work. I think everybody agrees here. So it's very hard to do this. Some people certainly have tried this. I have tried this. You destroy your whatever you are making. Don't try this with IKEA things, for sure. And this is also not going to work. So this means we need to use the right tools for the right purpose. For this, we need to be more educated, including the suppliers of digital tools. So we should not only focus on what's hot, but we should especially focus on value. Let's really go beyond the hype of digitalization, because if you too much focus on the hype, you can also destroy a lot of digitalization potential. And you might have people concluding it's not going to work, guys, even though it could have worked, but the wrong tools were applied for the wrong purpose. So this is what is called models fit for purpose. And I think very much the closing remark is that probably the future of digitalization will be a big toolbox. Often we are biased a little bit by what we sell, what we know as tools, but if we are realistic and look at the complexity of the water industry, we will need a very good toolbox of tools that are all in one box. You can just use them whenever you want, and they're working together. Okay? Thank you very much.
Thank you, Em, for the nice presentation and keeping your time perfectly. During the keynotes, or before the keynotes, Oliver mentioned that everything happens through the app, also asking questions to the speakers. Maybe I should have mentioned that before the first speaker, because if I'm looking well, I still don't have any question for Rem. So please, if you have any, just send it in the apps. While we're waiting for that, maybe I have a question for you. So you have a lot of experience, but definitely mechanistic modeling. You have a real long background in that. Also in artificial intelligence or data-driven models, I should say. You see this interaction between both of them. How do you see that in the field progressing? Do you see there's a playing field? Do you see utilities, competitors, academics? How do they go about this interaction?
Mm-hmm. Yeah, what I see when I especially look at the last 1 to 2 years, this means after a couple of years where we had first digital twin applications at treatment site, for example, people start concluding, some leading utilities and academics start concluding that hybrid models are extremely promising for the treatment sites. And right now we see an enormous increase in applications there. Yeah, so this means you apply a mechanistic model. We prefer the core to be mechanistic because that makes it explainable. And you get people along with it way faster compared to pure black box. But then, of course, you combine it with data-driven to have very good quality data. And, of course, for example, to go to auto-calibration, other type of functionalities, or model parts that cannot be modeled with mechanistic models. So either combine them, complement them, put them next to each other. So there are a couple of applications in the US, in Europe, right now, on full-scale plants where hybrid models are being applied. And that looks very promising. Yeah.
Okay, thank you. Well, we have our first question from Alexander Budrick, and I'm going to try to read that without my glasses. How do you get trust, or do you gain trust for data models and communicate with non-digital people in the field?
With non-digital people in the fields and the data-driven models.
Or Alexander, if you want to comment.
Yeah, the data-driven models. Well, it's more difficult because you cannot explain why a certain recommendation is being given. And if you ask me, that's one of the major limitations right now in adopting them at a very fast pace. For example, operators would see a threat. It's a black box that doesn't justify anything. And while the argument is maybe this value is better than the one we would have picked. Very hard because you cannot have a proper debate. What certainly will help a lot is validation, showing that if you're working black box, that of course the fits are there, that is at least doing what the plant is doing. This gives a lot of confidence. But again, we are of the philosophy that we try to prioritize white box models and only go to data-driven when it's really needed. Why? Because it's just more transparent and generically applicable. We try to prioritize them. For these reasons, for example.
Okay, and next question from Yanel Cialferez. What would you say is the biggest bottleneck to better exploit the interaction between the two types of models?
Good question. I think a good bottleneck is the mixture of skills. For example, data science, people that work on data science, I haven't met a lot of them that have a very good connection with the actual process sides, or the industry needs. While when you have mechanistic models, they need to understand it very well in order to build a very good mechanistic models. Of course, I haven't seen many mechanistic models that are also champions in AI and data science. So I think the biggest challenge is to bring people together, because one specialist will claim this tool is the best. This specialist will claim this tool is the best. When I talk to people in machine learning, they have no clue. They can't understand that tomorrow we can apply a model at the treatment plants without training it. So these worlds are so apart. They are so apart. I think that is the biggest challenge, to bring together these people and let all of them understand the real needs to solve tomorrow's problems first, then the day after tomorrow, and do it like that in a thoughtful way. So there's still some work to be done there.
Okay, we have another question from Sandra Ryan. What approach should we follow to ensure tools are designed that are fit for purpose, not too fancy, not too basic, Goldlock style? How can water sector professionals and digital tool developers work together?
Yeah, also a good question. Yeah, indeed, it's a big beast. When you look at digitalization, it's such a big beast. How do you catch it? It has so many arms, and if you look at how these tools can look like in 10 to 15 years, it's dramatically more impressive than if you would start tomorrow. I think the best way would be to start solving some acute issues tomorrow at the treatment sites, at the network sites. Some needs that are there tomorrow, solve them, and I think everybody will see what the value is, and take it from there. I think you can start with a very long-term vision, and that's very needed. But the application, if you ask me, should really start with solving problems, and solving them in a matter of months, not 3-4 years. In a matter of months, you have solved the first problems with new digital tools, and I think that's really a great start, because it will go automatic almost, I think. That's our experience.
Okay, someone who wants to submit the last question? Nothing coming in, then maybe I have a bit smaller, but what do you think so you had shown the interaction between the models, with hybrid models in between. Are there things, in your opinion, that both fields can learn from each other?
Yeah, I think for sure, 100%. Because mechanistic models, it doesn't mean they don't need any data. So, for example, you have really great tools at the data science sites to do very good data manipulation in an automatic way. I mean, this is utmost needed to the people at the mechanistic side. And I think the people at the mechanistic side can use those tools a lot to fast-track the learning of the needs side at the data science people, I think. So again, there's a lot of synergies possible. The methodologies are fundamentally different. So putting people together, I think, can be very powerful.
Okay. Please join me in thanking Wim